Epoxides are ethers found in a three-sided ring. They're found in natural products. This epoxide is an important intermediate in the synthesis of cholesterol. This epoxide from benzoate pyrene from cigarette smoke damages DNA. Here's another epoxide which produces brevetoxin B, which causes neurotoxic shellfish poisoning. Ethers are unreactive, but epoxides are much more reactive, which makes them very useful in synthesis. So stop the video and answer these two questions. For question 1, see ring strain in a three-sided ring. For reaction 2, note that the Grignard reagent is a strong nucleophile and reacts at this carbon here. This bond breaks to form this intermediate. Proton transfer occurs to produce the product. That this reaction is a substitution reaction. Note the structural features, the alpha carbon and the leaving group. We will look at two ways to make epoxides. One is the alkene plus peroxy acid. We will not be looking at this mechanism, but for the second reaction, alkene plus halogen and water, we will look at that reaction. So see practice problem 8a. So epoxides are more reactive than ethers, and they will react with nucleophiles to make alcohols. So stop the video and answer these questions. So the answer to question 1 is substitution reaction. And for a substitution reaction, we need an alpha carbon and leaving group. Here are the alpha carbons, and the leaving group leaves when either this bond breaks or that bond breaks. The reaction conditions determines the position of the nucleophile in these reactions. So let's apply your organic chemistry skills to predict the product of each reaction. So stop the video and work on this for a minute. And the answer is on the next slide. For the first reaction, note that the nucleophile reacts with the less substituted carbon and produces the alkoxide ion. That goes on and produces the alcohol. For the acid catalyzed reaction, note that the substitution occurs at the more substituted carbon, but it's only for tertiary compounds only. Note the stability of the tertiary carbocation. So let's practice your organic chemistry skills with these 6 reactions. Remember to consider the degree of substitution of the epoxide, as well as the nucleophile, and whether it's acid catalyzed. And the product is on the next slide. For the first reaction, note that the epoxide is secondary, which is the reason we get the same product for each reaction. For the second set of reactions, note that the epoxide is tertiary. So with the Br- nucleophile, substitution occurs at the less substituted carbon, but under acid catalytic condition, substitution occurs at the more substituted carbon. And for the third set of reactions, note that it's also a tertiary epoxide. And the nucleophile or acid catalyzed conditions determines the product. So epoxides are used to make epoxy glue. Stop the video and use curved arrows to show how each reaction occurs. In the first step, note that this is our nucleophile, so it will react with the epoxide. In the second step, note that another substitution reaction occurs. Note that these reactions occur many times to make the resin. And the hardener reacts with the epoxide part of the resin to form the cross links and make the cured epoxy hard. So for synthesis, we looked at 3 different ways to make a carbon-carbon bond. So stop the video and identify the carbon-carbon bond formation method you would use to make each compound. Since we've been talking about epoxides, let's see how this epoxide would react with methyl magnesium bromide. Note the methyl magnesium bromide reacts with the less substituted carbon to form this alcohol, which then can be oxidized to the ketone. For the reaction on the right, use method 2. First make an alcohol, then make an aldehyde, then use the Grignard reagent to make the alcohol, and then do an oxidation to make your product. So practice makes perfect, so see practice problem 9. The synthesis of lactulose A, an antibiotic, involves epoxides. So stop the video and use those curved arrows to show how this reaction occurs. So after the alcohol is deprotonated, we would expect the O- part to react here, but it actually reacts there. And in the second step, the O reacts where we expect that O right there to form our product.